So it's a great pleasure to have Artur Lopes in our seminar in Porto, temporarily on this virtual basis, and he'll talk about ergodic transport. Thank you very much, Artur.
Okay, thank you very much for the invitation. Thank you for all. I wish everybody is in a good health. And I'll try to talk about this.
Can you speak a little bit louder?
I'll talk about this topic. Is okay now?
Yeah.
I'll talk about a list of results in ergodic transport. It's more like a survey. I'm not going to prove anything. I'm just going to point out several results. And in my homepage that is mentioned here, there is a tilde missing before Lopes. You can find several results and things that I'm not able to have time to talk. Okay. Then just for the setting, X is a compact metric space given a continuous transformation with a node by MT, the compact set of t-variable probability measures. The classical ergodic system. And then, for instance, we consider several examples between then the traditional symbolic space with finite number of elements and the shift could be also results. These results are similar, also can be applied for S1 and D2-1 expanding map. Also the generalized XY model where M is a compact metric space and X is the space is the metric space to the power n, and the shift, most of the things apply. And we are going to use
Sorry, Artur, can you speak a little bit louder? It seems that your sound is a little bit low.
I'll call sigma star the set, the dual set. I mean, we're going to look at both sides, the future that is X and the past that is Y. And then we call later to appear more that we have the sigma that is shift and the sigma star that is also the shift, but the first one, sigma, is on the variable X and the second one is in the variable Y. This is our notation. And then the symbolic space 1 over d to the power z is the Cartesian product of these two sets, and use the notation of x and y. You have a pair that you point the left side, the what is in the sigma star, and the x is in the sigma, and we always use hat to talk about something that is on the symbolic space to the power z. Then any probability on this product space is called a plan. The classical reference for transport theory for people that are interested is the book of Delaney, Topics in Optical Transformation. Then I'm going to talk first about the classical transport theory. Then we have two probabilities, one on the x and the sigma, and the other is in sigma star, and k of mu1, mu2 is the set of probabilities in the product space such that project the first coordinate in mu1 and the second in mu2. Now, any probability on k of mu1, mu2 is called a coupling of mu1 and mu2. Consider a continuous cost function c of xy on the product, and then the transport problem is that given this continuous or upper semi-continuous, lower semi-continuous c, we are interested in the minimization of, you move all possible planes that project on mu1 and mu2, and you have the cost, and the big c of mu1, mu2 will be the infimum of this value for the transport. This is the classical transport problem. A probability n hat optimal on the product, which attains such minimum, is called an optimal plan for the transport C. Note that if you have C and you sum a function just of x, you determine the same optimal plan because you're going to integrate g of x among mu 1 and this is fixed. And if you also add cx1 to a function just of y, you get the same optimal plan, the same thing. Where is in the plan that realized this? You can think that C is the cost to bring something from X to Y, and you want to minimize the cost of going X, Y, given that you have two density of probabilities, one and two, that are fixed in the beginning. I wrote a brief survey called An Introduction to Coupling that appears on Modeling Dynamics Optimization, that this is the basic properties for someone that does not know anything about couplings, more in the language of ergodic theory, not because a lot of papers are in the language of probability theory. Sometimes this is a little bit complicated for me at least. And then this is for the dynamical system audience, introduction to coupling, several basic results and some new results. Then, for instance, you can consider the vastness metric. That's quite important. I mean, even two probabilities in one and two on a compact metric space with a metric D, you can define the infimum of the distance to the power P of all planes that project on mu1 and mu2, and you rescale by 1 over P, like an LP system, LP norm. Then omega P defines a metric on the space of probability, which is equivalent to E conversion. This is so-called the P Wasserstein metric. Omega 2, when P is 2 and P is 1, are particularly important. For instance, given a compact metric space and the associated space of probability measures with the metric W mu2, we can define a kind of Riemannian structure and you can consider geodesics. One of the problems that this space of probabilities is that this Riemannian structure requires some kind of Riemannian metric in some tangent space. And when the probability that we're talking about in this metric space has support in the whole space, then there is a tangent plane. But for instance, if you take a probability that has support in a periodic orbit on a small set that's not support in the whole space M, then sometimes there is no tangent plane, and this is a little bit awkward. And then after I understand a little something about this classical omega-2 Wasserstein metric, which I point out that there is no dynamic structure on this. This is it's purely measure theoretical setting, no dynamic. Then I was wondering what would happen if you would like to consider invariant probabilities and restrict the Wasserstein 2 to the invariant probabilities. The problem is that you can have probabilities on periodic orbits, and this is not good because there is no tangent plane on this Wasserstein space when you have norm of tangent vectors. Then it's natural to consider the same problem for Gibbs probabilities, because Gibbs probabilities for Holder potential have support in the whole space. And then in the case of infinite dimensional manifold of Holder probabilities, you can consider a Riemannian structure, not like on the vast space is not exactly Riemannian structure in the full sense that we are used. But in this infinite dimensional manifold of Holder probabilities, you can consider a Riemannian structure, and you can have vectors. And this asymptotic variance is basically the norm of the vectors. And this is on this paper on 2018 that we consider this infinite dimensional manifold of the probabilities and a Riemann structure, and you can have geodesics, you can have gradient flows, etc., etc. Okay. Then let's talk about the dual problem of this transport problem. Then the dual of measures, probabilities, are functions. Then a pair of measurable functions, fx and f sustenido y, will be C admissible, C is a cost, if satisfy this property, f star of y is the minimum among all x on the sigma of minus fx plus cxy. And then in this case, we have this f of x plus f sustained y is smaller than xy by definition. And then we call this pair is C admissible if this inequality for CXO is well defined. This is a kind of convex Legendre transform in some sense. That's classical in convex analysis. Then this is, there is a large reference of this in the book of Villeneuve. Then FC is the set of all C admissible pairs such that this integrals of f dim1 and f sustained of 2 are finite. And the Kantorovich dual problem is that given this cost function C that we just before considered the transport as an infimum, we are interested in the dual problem when we have a maximization. And then you define for each mu1 and mu2 the maximum among admissible functions of integral of f dim1 plus integral f sustained of mu2. The C admissible pairs help to find the solution of the main minimization problem. And this is like a linear program problem. You have a primal problem that you do not know to solve. Then you consider the dual problem that you also does not know to show, to have the solution. Then you put together the both, and then you are able to have conditions that help you to find the solution of the initial primal problem. Now, I'm going to talk about this. Then, under general conditions, the maximization of admissible functions is equal to minimization of probabilities once mu1 and mu2 are two Borel probabilities that are fixed. Then a classical theorem in transport said the following, that suppose that n hat is something that projects well, I mean, is a coupling of mu1 and mu2, and you find two functions, f and f sustenido, which is an admissible pair, and suppose that in the support of this probability on the product, you have that fx plus f sustenido y is equal to c of xy. Then if this happens, then good. You find the solution n hat, and this, the function f and f sustenido are both optimal. We should take care because the first problem that's minimization in probabilities, you have solutions. But sometimes in the dual problem that are measurable, sometimes you do not have explicit solution. I mean, you do not realize, but some f and f sustenido, but it's a infimum, and the infimum is okay. I mean, the result is this one, that dmu1 dmu2 is equal to c. Then the maximum is equal to the infimum. And this is very, very useful. I'm just telling you why in a moment. Then you have this admissible, and then this is called the selecting condition that help you to find the plan that is the solution, just trying to figure out in a smart way a plan that project and satisfy this equation. And then one interest in transport theory is that we are considering the relaxed problem. Then you like to know under nice conditions of the cost, if you have an optimal plan, that is a graph. A graph means that on top of each point, the fiber above the point x on the variable y, there is just one point with probability 1 for the plan on the Cartesian problem. This is a graph. If you have a graph, then there is a measurable transformation on the support such that the pullback of mu2 is mu1. Then it is interesting to find pullbacks, or how to find pullbacks of a certain probability given another. Of course, there is not always solution of this, but if c of xy is dxy to the square, that's the Wasserstein metric 2. For a large class of probabilities, given mu1 and mu2, you can find a plan, a transformation whole star that is a graph of this probability. That's the optimal sub-probability. And this is relation to probability that give zero mesh to small sets. Once I made the computations and the given probabilities of any holder potentials give zero mass to small sets if you are in S1. Let's say. I mean, here you are in a category of manifold or N or S1, not exactly on the symbolic space. That's what I'm talking. Then quantology duality for omega 1, that means when you put 1, not 2, the 1 is good to have geodesic symmetrics, and W1 is good because of the following. Remember, this is the definition of giving two probabilities, the infimum of dxy. And as I said before, the vast metric is equivalent to weak convergence of probabilities on this compact metric space. But it's better to have this metric given by the Cantor-Ropes duality, and I'll tell you why this is superior in several cases than the usual way to define probabilities by taking a dense set of continuous functions, blah, 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 blah. Then we can show that the W1 of mu x, that's an infimum among probabilities, is the supremum of functions that are Lipschitz with constant Lipschitz smaller than 1, and you take the integral of the difference of mu and mu. This is quite interesting result. It's a classical result. It's in the book of Villani. Why this duality is good? I mean, suppose you want that a certain sequence of probabilities mu n converges to nu, and you like to know its speed. Let's say you like to find that the speed is exponentially convergent. Then what I have to do is to find a smart plan Pn such that as this is an infimum, each time you have an n hat that's a plan, you have that this value is omega 1 is smaller than this. Then if you find small couplings, you can find this speed of convergence from above. And if you want to find something that this is really the speed, I mean, could be polynomial and you find this exponential. Then what you have to find is to find smart Lipschitz function phi n, because here you have a sup. Anytime you have a phi n, you have a lower bound. And sometimes you can control the speed of convergence of probabilities using duality. That's the reason why duality is interesting, important. And also the selecting condition is helpful. We can show, for instance, that the action of the rule of the Royal operator for a holder potential is a contraction for the one vast symmetric on the set of probability. This was proven in this paper, and we have to use exactly the duality. I mean, you have to use this supremum among Lipschitz functions. This is very useful. Then we can ask general questions like changing the topic, giving a probability mu1 that's not invariant, which is the invariant probability mu2 that is more close to W1 in the vast symmetric. That's another question. We want to find something that is stationary that's more close to this one. Then this is a problem that's not exactly suited with the classical transport theory. Then you have to consider ergodic transport theory that I'm going to talk about. Then this paper, this theorem by myself and Mengi, is the following. Suppose X is a compact metric space, Y is the Bernoulli space. You take a probability mu on the Borel measure probabilities on this compact metric space, and you take a cost, a continuous positive cost. Then for each plan, in each phi, we define something that's a little bit different from the that was before. I mean, the k of pi is the integral of the cost. This is the same as before. And then you have here, for each phi that's continuous, you integrate the phi with respect to mu. Then for this probability mu of x, we define p of mu sigma. There is no nu anymore. There is a sigma as the set of all Borel probabilities p on the product or the Cartesian problem that satisfy the following. The first coordinate is mu a that is fixed forever because there is a move that's fixed here. And the projection of this plan, which is in p of mu sigma, is a probability nu that is invariant. I mean, your constraint is that the projection on the x variable is an invariant probability that's now free to move. Before, mu and nu are fixed. Now mu is fixed, and the projection of the plane is nu, and the other projection has to be invariant probability. Then define the set of admissible functions that have to be changed now. The set of admissible functions are continuous function phi and psi, such that for all x and y, phi of x plus psi of y minus phi of sigma y is smaller than cxy. You see that there is a coboundary that appears here. Appears a coboundary on the function phi. Before, there was no dynamic, there was no sigma. And there is the definition of the admissible functions. Now, phi is a function, and psi minus psi sigma is a cobounded to zero function. This is the final set of admissible functions. Then you can show that the infimum among all integrals with respect to all probabilities that are first coordinate nu and the second is invariant is the sup of the integral of the admissible function. I mean, this is analogous to the previous results, but now you have a dynamic context because you are asking that the new projection is invariant. Then the left sign is attained by a probability Q of optimal. So that's easy. And if it is Lipschitz continuous, then there is Lipschitz function phi and psi, which are admissible realized of the supremum. Remember that not always these admissible functions realize the supremum, but now we have Lipschitz functions that are phi and psi that are admissible realized. But I'd like to point out that all this is nothing else than a generalization of ergodic optimization. This is more or less like you have a function that you want to maximize that is random. Is random to according to the variable y that is described by a probability mu. If mu is a delta Dirac in a certain point, then the plan cxy is just a function of y, and all this infimum is a minimization. And this condition of the admissible is nothing else than the coboundary subcohomological equation for the eigenfunction, for the subaction, I'm sorry, for the subaction. I mean, this is generalization of ergodic transport that your cost is random. Then I'm going to return to the problem that I initially mentioned, that what's the probability mu2 that's more close to a certain probability mu1? Then for fixed mu1, you consider the Wasserstein integration of dxy and take all probabilities, all plans on the product that the first projection on the variable x is mu1 and is invariant for sigma. You do not fix the other variable. Then in the set of all probabilities, such that the projection on the x variable is p1 and the projection on the y variable is nu, which is invariant, then there is an optimal plan which realizes this infimum. This is obtained by a certain plan that I'll call optimal. And in the support of the optimal plan is contained in this set. That's why it's good the selection condition, because sometimes it's difficult for you to realize which is the plan that realizes this optimal. But then the selection condition gives you that if you find a probability, a plan that is contained in this set, and phi, psi are admissible by definition, then you find the support of the probability on the product. And then if you take the projection mu2 of this optimal, then you're going to have a probability mu2, and this mu2 is the invariant probability that's more close to mu1 in the Wasserstein metric. You have to go to the plan, and then from the plan you find the the more close probability to move to move on. And I'm just saying that this X condition is helpful for you to sometimes realize what's the solution. For a general function C of xy, suppose C is just depend on y, then consider the infimum of k pi, the transport problem with dynamics, that is on the left side, is equal to infimum of the cy, because there is no, there is an integral missing here. Infimum of integral of cy dpy. And this is phi that we get is a constant, and C is a subaction, and you are in ergodic optimization setting. Just to briefly remind you of this kind of results. Suppose X is the symbolic space. Given a continuous potential, we denote MA, the maximum of the integral of AX among all invariant probabilities. This is one of the purpose of ergodic optimization, to understand the probabilities that attain this supremum. And we are interested in the characterization properties of A maximizing probabilities. That means the probabilities mu that satisfy that the integral of the probability is equal to the maximum value, that's M of A. If so, assume that A is holder, then there exists subaction. So a subaction is a function such that satisfies this inequality. Is a kind of subcohomology equation. V of sigma minus V minus A minus MA is bigger than 0. And the support of maximum probability is contained on this set. This is a classical result in ergodic optimization. This is nothing else but more than this Lexer condition of transport theory. In the previous notation, the C of X is AY, the Psi is V, and the phi is a constant. Then all this transport problem with dynamics contains ergodic optimization. Then let's talk briefly about another kind of problem. Maybe most of you know, but I'm going to repeat for people that are not familiar. Given a potential, the whole operator acts on continuous functions, psi, like given a function psi, you take a function phi, that is the sum on the preimage. You put a symbol A before any x and take phi of x. And the whole operator is quite important for understanding equilibrium probabilities and other results are important in the thermodynamic formalism. That is a mathematical version of statistical mechanics, let's say. Then we are interested in here the subaction, the support of maximizing probability is contained in this set. Then I said before, C of AX is this. This is the Wheel operator, and the Wheel operator acts on probability via the His theorem, indeed, giving a probability nu. You take the function of that, take phi to LA of phi dx, the mu x, and this is a bounded linear function operator. And this defines a probability by His theorem, and this by definition is the image by LA star of mu, is the probability mu that realize this bounded linear function operator. Then the Wheel operator said the following: given a Holder potential, there exists lambda a, it is the eigenvalue, and a positive eigenfunction, phi of a, such that L of a of phi of a is lambda a phi a. An eigenprobability, rho a, such that for the same value lambda a, A of rho a is lambda a rho a. This is like the Frobenius operator that you have. If you have a positive matrix, we have a left eigenvalue and a right eigenvalues, right eigenfunction, and a left eigenvalue, and a left eigenvector and a right eigenvector associated to the same eigenvalue. And this is the infinite dimension of this. And you need to assume regularity, that's a potential holder. And if you take the product of phi a, that's a function, in a way that's probability, the sign probability, if you have to normalize, you find that this probability mu A is called the equilibrium probability. That's maximized pressure. That's the right result. And for A fixed, you can multiply the potential by beta, is a parameter, and consider the eigenfunction phi beta A for the new potential beta A, and the eigenprobability rho beta A for beta A, and the equilibrium probability beta A. And then you have lambda A, LB of A, all this that you are having in the well operator, but now this indexed by beta, because A is fixed. And beta in statistical mechanics correspond to 1 over temperature. Then a different kind of problem that I'm going to talk, because this is related to what I'm going to talk more in the end of our talk. For each x, we define the function e of x, that is the sum from 0 to infinity of v of sigma minus v minus a minus ma. Remember that this is positive if v is a subaction. And then you are summing this in the orbit sigma n of x. And this is a positive function. This positive function can be infinite. But once you begin in the support of maximizing probability, sigma n will be on the support of probability, and this will be always 0. Then this function I is 0 on the support of the maximizing probability. Could be 0 also in other points. This can happen. But is a lower semi-continuous function that can have infinite values, but defined in the whole space sigma, that is symbolic space. Then repeating, I of x is a function from x to the real that sum in the orbit this co-boundary equation. V of sigma minus v minus a and a. This is a function on the symbolic space that can have infinite values sometimes, but is 0 on the support of maximum probability. Then suppose that the maximum probability for the potential A is fixed. Then we get the following. The Gibbs probability move beta for beta A, we're moving beta. For each beta, you have a probability mu beta that's equilibrium for beta A. Then it's known that mu beta converts to the maximized probability when beta goes to infinity. Then you can ask about large deviations, not on time, but large deviation on beta. Large deviation on the temperature. Because when mu beta goes to mu, you want to know what happened with the cylinder, the measure of cylinders. Suppose you have a cylinder that is not in support. This will go to 0. But what is the speed of convergence? Then we can ask, as I said, large deviations not on time, not on n, but on beta, on temperature. Then the deviation function E is non-negative, as I said, lower semi-continuous, and 0 on the support of mu. Then we have this result that says that if the maximized probability is unique, then for any cylinder set C contained in the symbolic space, if you take for C fixed the mu beta probability, take log of mu beta and divide by 1 over beta, this is equal to the infimum of I of x on the cylinder C. This is, you can imagine a picture like I of x is a function that is 0 just in the support and is positive outside. Then if you take a cylinder outside the support, there is an infimum of this. The values that are infinite does not matter because you want to take an infimum. In each cylinder set, there will be at least one point such that I of x is not infinite. Then you can know the speed such that mu beta c goes to 0 on the log, on the exponential velocity, knowing the infimum of the I of x for c on the cylinder. This is a large deviation on temperature, on beta. Okay, then let's go to dual problems. I like very much dual problems. Then take sigma star, the dual subshift. I mean, it's a copy of 1 over d to the power n with the shift. And we consider the extended dynamic, the network extension, that will going to act on the product of sigma star and sigma. And we use the notation of y, writing on this from left to right, from right to left, y0, y1, etc., and x0, x1 from left to right. Then the elements on sigma hat can be expressed like in this way. There is the future that is x and the past that is y. This is a notation. Sometimes I use this notation. Then you have the sigma hat, because everything that is on hat on the power z has to be on with hat. This is the shift, the usual shift on the symbolic space 1 over d to the power z. Then the inverse is just move the y0 for the right. Our notation, next result will claim things about the sigma hat 1. Again, we have the following problem. Given a potential A defined on sigma, we want to find a dual potential. The dual potential I call A star Y is defined on the dual space. Then we say that A star is the dual of X, and I'm saying A is in the variable X and A star in the variable Y. Okay. Then we say that A star is the dual potential if there is omega, it's a function from the product X and Y on R, such that each time you take a symbol and 2 points, you have this equation. I mean, here you put A, and here you put A for the other side. Okay. This can be expressed using the sigma hat minus 1, okay, but it's more simple to see like this. Okay. In principle, you could say, oh, okay, why this? Remember the following. Suppose you have a potential that depends just on 2 coordinates on symbolic space. This is A of X. The transpose of A of X is to substitute A sub ij by AJI. I mean the transpose. Okay, but suppose now you have a potential that depends on all coordinates. What will be the transpose? You cannot do this or take a matrix and take the transpose of the matrix. Then this is the natural concept to consider as the transpose of a matrix, but now it's an infinite matrix with a countable number of entries that are the coordinates. Then this is called omega is called the involution kernel for A. And the evolution kernel is something very, very useful, and it appears in a natural way in several situations. But what I'm going to talk about now is just some of this information. Then the involution kernel is a function from the sigma hat to the reals. And if A is Lipschitz or Holder, we can show that there is a Holder function A star of Y, and there is a B Lipschitz function omega of XY that satisfies this equation. Okay? The point is that what you want to do with this equation. I just point out that if you take that omega and A star correspond, omega is the dual involution kernel, A the dual potential correspond to A. If you multiply by beta W, beta A star correspond to beta A. It's just multiplying all this by beta. Then this is very natural to use when you want to make temperature go to 0 or something like this. Then I just like to mention, not directly to this, one of the important uses of the entropy production is that this I learned very recently from studying some papers on entropy production, is that on this paper by myself and Mengi on information gate Quebec Libre divergence entropy production in evolution kernel, we show that the evolution kernel is absolutely suitable and natural to be introduced to understand entropy production. Entropy production is can be defined, can be understood using the evolution kernel that exists when potential A is Lipschitz, and then A star will be the dual potential. Okay. Then we denote by ρ A and ρ A star the eigenmeasures for LA and L star as before. I'm not going to multiply by beta at this moment, okay? A and I star are fixed. Then suppose that C, I'm going to talk about why, what was the initial reason for understanding omega of the evolution kernel that's in the paper by Vieira, Lopes, and Tulane that I just mentioned. Then suppose C is a constant and omega is the evolution kernel, and we take e to the w I y x, and this C here is just to normalize, because you put here ρ A of x and ρ A star of y. Okay, it's just a constant to normalize. In order that this integral e to the w y of x, the ρ A star of y, the ρ A of x is 1. Then, if you call kx this, then the probability mu A of hat that multiply this k of x, d ρ A star of y, and ρ A of x is the natural extension of the probability mu A, and is invariant for sigma hat. Then this is a natural way to define the solution of, suppose you have a potential on the, lattice 1 over d, 1, 2 to the power z, and then you take, like in Parry Polyquat book, the potential that depends just on one coordinate. Just depends just the feature on the x, and then you use Ruel-Perron operators. Then you want to come back to the initial probability on the lattice 1, 2 to the power z. Okay, a natural way to do is to use this. And here is the main use that we find for this evolution kernel. Then k of x is e to the power omega. Then this k is an integral kernel that transforms the eigenprobability for the potential dual A star on the eigenfunction for the potential A. And this is an integral kernel that transforms past in the future, because past is on the variable y and x in the variable phi. By the way, we can say that, let's come back here. You see here, we say that given A, the potential A star of y is the dual potential if satisfy this. We say that A of x is symmetric if A star of y is equal A of y. This is like the matrix to be self-adjoint or equal to this transpose, equal to the transpose, right? It's strange, but a lot of potentials satisfy this symmetry. For instance, minus log of T prime for expanded transformation in general is symmetric. I mean, the dual is also minus log of T prime. And it's strange, but you can compute in several cases explicitly the omega. This is strange, but sometimes you can explicitly the omega. And to compute the omega is more simple than to compute the eigenfunction. Sometimes you can compute the eigenfunction. You cannot compute the eigenfunction explicitly, but you can compute the omega kernel involution explicitly. Several times you can do that. Okay, if it is symmetric, then LA is LA of star, and then rho A star. Then here you could have that the if you take the eigenprobability for the Whelp rate for A, assuming that A is symmetric, then you obtain the eigenfunction. And then this is the main eigenfunction for the Whelp operator. And you have this symmetric result. And this involution kernel connects past and future. And then now you can realize the following. If you take multiply A by beta, then you multiply beta A star, and you multiply the eigenfunction by beta, the involution kernel by beta. The C now depends on beta, but the C is the normalization. And then if you want to find, I'm going to come back. Here, if you want to find the speed that mu beta goes to 0 for a certain cylinder state, you need to know the eigenfunction and the eigenprobability. And you have to make beta goes to infinity. Okay. And then the initial way to obtain the deviation function was using the involution kernel. The involution kernel was presented for the first time for this reason. And then, of course, in the proof of this, we have to use this expression. Because here you have phi beta. Here you have rho beta. And you have the kernel that has the power beta. Then this is like the asymptotic of a function, of an integral function that has a beta on the power, and then use something like classical Laplace method. It's not Laplace method, it's more sophisticated. The idea is something like Laplace method. You have a parameter that's going to infinity. Then everything is going concentrated on the infinite of something. And then the eigenvalue of the lambda A star are the same, and you can have the eigenfunction from the eigenvalue. This is a dual problem. Then let's come back to ergodic transport. Then you have M of A is the supremum of the function A, and M A star is the supremum of A star. I mean, you have ergodic optimization for A, and for the dual problem for the dual potential A star. Suppose the maximized probability for A is unique, denoted by mu state R infinity, mu infinity A star, for the potential A star, and V star calibrates reaction for A star. What I'm saying is the following. I have A and A star. I have V and V star. I have dual problem. And the evolution kernel is the thing that connects both things, right? Then, repeating. Suppose the maximum probability for A is unique, denoted by mu infinity A star. The maximum probability for the dual potential. Now I'm not anymore in ergodic thermodynamic formalism. I am back to ergodic maximization. Now V star is the calibrated reaction for A star. I then calibrate this reaction as a kind of subaction. Then it's true that MA is a M star in any case. And there exists a sigma invariant probability on the product such that projects on sigma on the maximized probability for A in one coordinate and in the other mu A star in the other coordinate. I mean, have a plan that project on the maximized probability for A and the maximized probability for A star. Then, on the support of this sigma invariant probability, the invariant shift, we have that in the support of this, in this paper by Lopes, we show that Vx plus V star of y equal Wx minus gamma, where G is a constant, is true. Okay? At this moment, we didn't know anything about transport. We didn't know that this is nothing else than the slackness condition for the cost W. Okay? Then after some study in Ergodic Transport by the book Villani, we realized that the duality of A star, V star given by W is associated to a Ergodic transport problem. Let's see. Then suppose you take the set of plans that is a coupling of mu infinity and mu infinity star, that the two probabilities maximizing probability for A, maximizing probability for A star, take all plans such that project correctly. Then consider the cost C of xy as the minus wxy, where W is the involution kernel for the Hodel potential A. Then you consider the transport problem. I mean, all probabilities that are projecting right on mu infinity star for the cost minus wxy that I'm going to call x. And the important point that I mentioned before, there is no problem if you sum I of x, the potential, because this is a function just of x. As I said before, the infimum of this is the same. Then let's put here, and then the probability that assume this minimum is called the optimal transport for C, where C is the minus the involution kernel. I take the infimum. If I want to put the sup, then it will be the involution kernel. The cost is minus Wi. Then you have a probability on the product. Okay? Then you want to stress more and more the duality. Then what I was just saying, that C hat, that is the same plan, but adding a function just y, does not change with the plan. And this probability to hat, it will be invariant. Then we have this theorem that says the following. Given a Hodel potential, consider the corresponding subaction minus V and minus V star, define an optimal pair for C hat. This is the result. Therefore, minus V and minus V star and the maximized probability mu r and mu r are dual objects. The optimal plan is the natural expansion of the maximized probability for A. What I'm saying is the following, that V, A, and A star are dual. Rho A and Rho A star are dual. And the subactions for V and V star, for A and A star, are optimal pairs. That means the Ergodic optimization is inside this result in terms of duality. I mean, V star, the subaction, is V and V star are optimal planes. Another theorem says that in the case of the shift, if the involution kernel omega is twist, I'm going to tell briefly what's twist, that I'm just finished. Then the minimizing probability for the cost is a graph. Therefore, up to 0 mirror is a graph. That means one of interesting things in transport theory is to find that your optimal plan is a graph. And just for the record, something that's not exactly about this, you can consider thermodynamic formalism for plans. And this paper, Entropy, Pressure, and Quality for Gibbs Plans in the Ergodic Transport by Lopes, mainly more and Joanna, we show that you can extend the thermodynamic formalism for plans. I mean, the Gibbs probability to be a Gibbs plan for a potential C of xy. And then I'll finish here. Thank you very much for being present. Thank you.
Thank you, Artur. We have some time for questions. If someone wants to make a question, just to unmute your microphone, please.
What? Any questions?
So while people are thinking, let me ask you one thing. I got curious. Is in some sense the maio conjecture that minimizing or maximizing measures for typical observables are concentrated on periodic points. They would have a representation on the supports of these plans to be concentrated on graphs. So is this twisting condition for the kernel typical among the cost functions?
Good questions. I just mentioned that because I have a new transparency for people. I mean, given the evolution kernel, let's say that we are in the symbolic space, we have a lexicographic order. Okay. And then we say that evolution of a function satisfy the twist condition if the evolution kernel is continuous, satisfy the evolution kernel if each time you have points A, B, and A prime and B prime with A prime bigger than A and B prime bigger than B, then you have this inequality. This inequality means the following, that if you want to find the infimum of the suprema, don't remember, of omega, you have that, if you have points that are here on the diagonal, if you change input here, okay, the anti-diagonal, this is better. And this makes the support of the infimum probability for integration have to be more or less like when you go from left to the right, the support have to be increasing because otherwise you change. Okay, and the twist condition plays the role of the convexity on Aubrey matter, because in ergodic optimization you do not have convexity. On the Aubrey matter theory, you know that the matter measure that is a probability on the tangent plane, on the tangent bundle, project on a measure on the manifold. And for this you need to be a graph. And in the proof you use convexity. But in ergodic optimization you do not have convexity. Then what you're going to say is that you can replace convexity by the twist condition, but you have to use also the dual to do that. And then the twist condition, and not all potentials A is such that the dual potential satisfy the twist condition. It's not true. But there is a paper by myself, Contreras, and Elismar Oliveira that we show that generic properties for omega for the generic potential A. It's another paper that I did not mention. It's a paper by Contreras, myself, and Tulane. And Contreras, myself, and Elismar Oliveira, where we show that for a generic A, you have some properties for the involution pair. But this is not directly to the Contreras result about that the support of maximized probability generic is in a periodic orbit. It's a different thing. Okay. You can also have this condition on the space 0, 1. That is just this. That is like a twist condition, really a twist condition on the interval. And this is just symbolic version of this.
Okay. Thank you, Artur. Any other questions or comments? Okay, so if not, let's thank again Artur. Thank you for this talk.
Very much. Thank you very much.